And we're back. Welcome back and happy Thursday. Today, we'll do a number of things. We'll touch on feasibility of learning and build up a framework making use of Hoeffding's inequality. But before we do so, some administrative bits. The reading is from the main text, Learning from Data, Chapter 1 up through Section 1.3. So from before, when we last met, we talked about the architecture or anatomy of a learner, and we talked about those components you have control over and those you do not have control over. You have the unknown target function, which is out there, but you don't know what it is, and it's working in the background, outputting or associating labels with training examples. You don't have control of the training examples. Those are your historical records. But you do have control over the hypothesis set and learning algorithm. The hypothesis set is a set of candidate formulas that you search through by the action of a learning algorithm to find the final best hypothesis that most closely mimics the action of the unknown target function in associating labels with training inputs. And so together, the hypothesis set and learning algorithm form your learning model. So you're given historical data, you have your target function as a reference, and the idea is that you want to input a new record and output from your final best hypothesis some predicted output that is coincident with the actual value of the label associated with that new record. In essence, your model should make the correct output. Your final best hypothesis should output the correct output on new data. And that on new data part is very, very important. And so the question then is, can we really learn? You have a function, your unknown target function. You don't know what that is. Okay. You have a finite data set in your historical records. And the ask that we have for this system, what does the function do outside the data set? That's what we're after for your final best hypothesis. If the target is truly unknown, it could, your target function, assign any values outside the data set. And so the linear perceptron, we know, works because of this geometry of the data. That's an assumption that the data is linearly separable, right? That's a prerequisite. Perceptron will still try to classify data that's not linearly separable, but it doesn't do well. It's not guaranteed to converge on a very good final best hypothesis. And so let's take a look at a bounding approximation, and then after that, we will switch to Matlab and actually show you an example of the Perceptron learning algorithm. So let's take a look. So let's imagine we have a vase or an urn, and that urn is filled with marbles. These marbles are colored either red or green. And let's assume a parameter mu governs the probability of picking a red marble, so that mu represents the proportion of those marbles inside the urn that are red. Now, of course, I have to show this to you and display it on the screen, but let's imagine when you take a marble out of this urn, you take a marble, you write down the color of the marble that you got, and you put it back into the urn. You return it to the urn. And so let's define mu to be the probability of red marbles. And therefore, law of total probability says that the probability of then picking a green marble, if the colors are only red and green for the marbles in the urn, is 1 minus mu. Now this parameter mu is the actual parameter value known by the process, stochastic process, that assigns colors to all possible marbles. And in effect, what we're going to do is draw samples. And when we draw these samples from the urn, so you don't know what the colors are, you reach in, you pick out a marble, examine the color, write it down. Now we're going to define another parameter, and this parameter is computed over your sample points. So let's call those sample points your out of sample points, and let's call the marbles that are in the urn the in sample points. So you have your points out of sample, and conversely, the probability due to law of total probability of picking a green marble is 1 minus mu. Now, let's add a definition. Let's define those marbles that are in the bin as so-called out-of-sample points. And this parameter mu is the actual value associated with the population process that assigns colors to marbles. This population process is out there, but it's unknown by us. There certainly is a proportion mu, but we don't know what it is. So when we draw a marble and we examine it and write down the color for that marble and return it back to the urn, we're going to call that sample the in-sample points. Those marbles that are in the urn, because they're not part of the sample, we're going to give them a name. We're going to call those the out-of-sample points. And so for your in-sample points that you get when you write down those samples for the marbles selected from the bin or the urn, we're going to compute the proportion of those in-sample points whose color was red. And we can do that by just counting the fraction or the number of red marbles. So let's define another quantity. Let's call that nu. And nu is going to be the fraction of red marbles. So in essence, what we're doing is we're communicating with this unknown population process associated with the marble color for the bin or the urn. We're communicating with it through its samples. While we don't know what the proportion is, when we sample and we examine the marble color, write it down, and then compute the proportion or the fraction of red marbles in sample, we're communicating through the samples. We're communicating with the population process. So the population process is telling us something about itself through the samples that we pick. So let's further assume that when we pick marbles out of the urn, we independently pick n marbles or samples. And when we do that, we compute the proportion of red marbles, and this is our mu, how we calculate it. So the question then one might ask, does nu tell us anything about mu? Well, since you're sampling, you might think yes, but you're replacing, and you don't know from where you're sampling. It's random sampling, uniform at random. You're not preferring one marble over another. So you don't really have control over what particular samples you're getting. So then one of the questions you might ask is, when does nu tell you something about mu, and when does nu not tell you something about mu? Because one thing that can happen is you can have a mixed blue-green set of marbles in the bin, but your sample can be very different from those proportions you see in the bin. You could also have a sample that is mostly green, so the proportion nu is going to be very small, and at that same time, the proportion for the bin is mostly red. That mu is much closer to 1, or vice versa. And so while that's a pathological example, it could be that when you take your in-sample points from the bin, it could be that you tend to pick among a small number of marbles, this one, this one, this one, this one, and you end up with a higher, unnatural, as it were, representation of the red marbles versus the true proportion across the entire population of marbles in the bin. And so this has to do with this idea of what is possible versus what is probable. Now, is it possible to pick every single draw this red marble? Well, yes, it's possible. Is it going to happen very often? Not very often, but it's still possible. And so this idea about what is possible versus what is probable has a lot to do with how well you can learn if learning is feasible. And so let's make this sample size n, the number of in-sample points, very large. So n, the number of samples in sample that we draw from the urn, is going to approach infinity. Now in this particular case, as n goes to infinity, the sample size of the number of in-sample points, our sample, nu, is going to approach mu. And why is this? Why does that happen? Why is that the case? Well, this idea that we talked about when we said the population process is communicating with you through the samples. And let's think of what happens with a presidential poll. Now, in a presidential poll, you call some number of households, maybe 1,000 households, and you ask them, who will you vote for? And they tell you, and then you report that so many percentage of people want to vote for candidate A, and so many other percentage of people want to vote for candidate B. Now, of course, if you were able to call, theoretically, every single household that was eligible to vote, then that would be the precise proportion, and also assuming that they're not lying to you or being dishonest. But let's assume everyone's being honest. But if you were able to administer this poll and sample everyone who's eligible to vote or everyone who will vote, that would be a precise representation. Because you're telling you, this process, what it's going to do in terms of the assignment to color, like a vote, for every single out-of-sample point inside of the urn. And so when the in-sample sample size is infinite or gets large, you get a much more precise coincidence, and therefore nu tells you a lot about mu, and nu approaches mu. And this is very similar to what happens between the final best hypothesis and the unknown target function. The target function essentially has an opportunity to tell you what the output is, that class label, +1, -1, associated with every single input. Now, of course, if you had an infinite number of training examples, an infinite number of historical records, well, then the target function would be telling you, here's the label for every possible input. The target function would be telling you what the label is for every possible input available. Now, certainly, that's not possible. It's theoretically sound, but it doesn't happen in practice because the set size for your in-sample points is not infinite. In similar fashion, the historical records in the anatomy of a learner is never of an infinite sample size. So for large n sample size, nu, the proportion for the in-sample points, approaches mu, the unknown proportion for the process associated with the out-of-sample points. So in essence, what we say is for large n, nu gets close to mu, it approaches. Another way of expressing this idea of nu approaching mu is that nu is within some error tolerance, epsilon, of mu. So we can also express this probabilistically. We talked about what is possible and what is probable. And so because it's not always the case that you're going to pick a particular pathological set of marbles out of the urn, you have to use the framework of probability to talk about what is probable. How likely is it for a particular type of coincidence between nu and mu to occur? So probabilistically, you would say you want to make sure that the probability of something bad happening is small. Now, something bad happening is that case, that pathological case, where you're picking from a bin where a large proportion of the marbles are red, but the samples are mostly green. So it's possible, but it's not highly probable. It's not going to happen very often. So you want a framework, probabilistically, to say something that says, let's minimize the possibility of something bad happening. So you want the probability of something bad happening, some expression for bad things happening. That event, you want that probability, or the occurrence of that event, you want the probability to be small. So in essence, how you can do that is by bounding that probability. It can be no bigger than a certain amount. Now, of course, when you bound it, you want to make sure that the bad thing happening is a description of the coincidence or the error tolerance between nu and mu, your in-sample proportion and your out-of-sample proportion, mu, which is unknown. And so this idea of bad thing happening, we're going to encode that mathematically or express it as this idea of being far away from tolerance, that nu does not approximate mu very well. So let's take a look and try this out, see what happens. So we say the probability that the difference, and we don't care whether it's a positive difference or negative difference, a positive tolerance or negative, so we express the absolute value, the probability that the difference between nu and mu exceeds some error threshold, meaning that the probability for this event that nu's difference from mu violates this tolerance epsilon. It's far away from tolerance, the coincidence between nu and mu. Now, the good news is there's a framework for doing this. The weak law of large numbers makes use of the moment generating function, and this has a decaying exponential. So the bound on this error tolerance, this probability of something bad happening, is at most e to something proportional to e to the negative n. And so absolutely, we said the more examples you have, the more marbles you choose as n goes to infinity, well, this probability should get very, very small that the error tolerance is going to exceed this threshold epsilon. Now that goes to the weak law of large numbers that says in expectation, the average, if you have the number of samples large enough, the average is going to approach the true mean, where this parameter mu is the true parameter, the estimated parameter is this nu. And so this inequality has something to do with the weak law of large numbers, and we won't go into that, it's beyond the scope of this class. But the good news is the probability that nu coincides with mu that is violating or exceeds that error tolerance epsilon is going to be at most a decaying exponential with respect to the number of samples. Now, this is the probability of being outside a specific error tolerance, and it gets smaller with more samples. And it fits with our definition where we said as n goes to infinity, that nu approaches mu. But there is some bad news. Let's hear the bad news. So the good news is that we can get good coincidence between nu and mu, our in-sample proportion relative to our out-of-sample proportion, where out-of-sample proportion mu is unknown. We can make that small, or the likelihood that we're going to violate that error tolerance, we can make that small by just increasing the number of samples. But there's also some bad news. Well, it depends on the tolerance. And so with this tolerance, it modulates the sample size through a square term. And this is the probability of being outside a specific error tolerance within that tolerance epsilon. Now, there's a trade-off here in that if your tolerance is very, very small, epsilon squared is going to be very small, and you're going to need a very large sample size for the action of that decaying exponential to be small enough that this coincidence between nu and mu, the in-sample proportion and out-of-sample proportion, of violating this error tolerance. And so in order to very rarely violate this error tolerance, you have to make your sample size even larger. If you relax the tolerance, well, now you don't need as many samples. And so a very tolerant scenario is one where epsilon is closer to 1, and a very non-tolerant scenario is when epsilon, your tolerance, is very close to 0. And so if you want the coincidence between your in-sample proportion nu and your out-of-sample unknown proportion mu to be very, very close to one another most of the time, you need to balance between how close you want the coincidence with the number of samples you're going to take in sample. Now, it's important to remember that all you have are the samples. You don't know what mu is, but you do know that if you want a certain coincidence or tolerance between this known nu and this unknown mu, you can get that strong coincidence. Most of the time, it's highly probable that the bad thing will not happen, or the bad thing happening will be a very low probability, meaning good things will happen most of the time. You can do something about it by making sure that you have enough samples. So this is the basis of something called Hoeffding's inequality. And it comes from the weak law of large numbers. And we have a decaying exponential because that has to do with expectation, which is a moment, a probabilistic moment, which has an exponential form to it. And so the full form of Hoeffding's inequality, and you'll just have to take this on faith, well, it's actually true. In another sitting, if time permits, maybe we will, maybe we won't, go through the derivation. But what Hoeffding's inequality says is that the probability of that nu, the in-sample proportion, coincides with this unknown out-of-sample proportion, that the coincidence will violate this error tolerance, the bad thing happening, is no more than 2 times e to the minus 2 error tolerance squared times n, the sample size. So this comparison between nu equals mu is part of what's called the PAC framework. They're probably approximately correct. It's close to, nu is close to mu some or much of the time. Now, the probably part has to do with the probability bound. The approximately part has to do with the error tolerance. And the correct has to do with this coincidence between nu, our in-sample proportion, and our out-of-sample proportion. And so this is valid, Hoeffding's inequality, for positive n, the sample size, and for epsilon, the error tolerance, greater than 0. Now, this is not asymptotic, but it holds for all such values, instantiation of n positive and non-zero positive epsilon. It holds for all such values. It has an exponent, so that's desirable. You know that it decays very quickly. It comes from the law of large numbers, and you're bounding it uniformly. So it doesn't matter if nu and mu is bounded from above or below. It's an epsilon ball, so to speak, and that bound is in all directions around mu. And so this is from the law of large numbers, and it introduces a trade-off. We have a trade-off between n, the sample size, and epsilon, our error tolerance. If you want a stricter tolerance, you pay for that with more samples. So what does that mean to our anatomy of a learner? It says that if you want a better final best hypothesis, and we'll relate this in a few modules later, if you want a better final best hypothesis, that corresponds to the performance on your historical data, your in-sample points. Your data, in-sample points, historical records, has to be a large enough data set in order to get good coincidence between what you know and this unknown, this target function. And so for Hoeffding's inequality, it governs the feasibility of learning and defines the trade-off between this notion of error tolerance, how closely what is known coincides with what is unknown, and the sample size, n. So you need more samples to pay for a stricter tolerance. And so we say that nu approximates mu implies that mu approximates nu. Now, of course, we say that nu approximate mu because we have no control over nu. Nu is that governing parameter out of sample for the proportion of red marbles in the bin. You don't have control of that. So if they're close enough, you can just invert the logic and say, well, if nu approximates mu, that means mu also approximates nu, even though you don't have control over mu. So you can use Hoeffding's inequality to show how nu affects mu, but the actual case or cause is the other way. The form is symmetric. So you're saying, okay, well, I can only do something about out of sample. So if I can get out of sample, in sample, and out of sample close enough, then I can just say the out of sample mu I know is going to be close by what's in sample proportion nu. So I can say the out of sample mu is going to be close by nu. If I know nu is close to mu, then mu is certainly close to nu. So nu is close to mu. I know nu, and now mu tends to be close to mu. So this proximity argument allows you to talk about either one, even though you don't know what the mu parameter is. Okay, so we're going to stop there for now and transition to Matlab to have a little bit of a tutorial about Matlab and show an example of the Perceptron Learning Algorithm. So I will meet you in Matlab. So we are in Matlab, and I brought up a module, test PLA. But before we go over that, I'm going to bring up so we're in Matlab, and I've brought up a test PLA file to show you Perceptron Learning Algorithm in action, or a version of it. But before we do so, let's go over a little bit of some Matlab constructs. So I'm going to go ahead and create a new file, and let's call that Matlab Intro. And Matlab consists of the runtime environment as well as an application development environment that you see here that allows you to edit programs. The syntax of Matlab, Python is very similar. I'll say Python is similar to Matlab, then Matlab is similar to Python because Matlab has been out longer. And Matlab has the usual constructs like loops and functions and conditionals that most programming languages have. Now, in Matlab, the system is very, very good with matrix vector algebra. And so how you define a vector, let's say vector is equal to 1, 2, 3, 4. Now, I've just defined a vector. A vector is nothing more than an array of numbers. So if I type vector, well, that gives me a row vector. And so when I specified with square braces the definition of my vector, I'm actually defining the individual columns for my vector. So I can change it 1, 4, 5, 1, 4, 5, 7, and I can rewrite my vector, and it will update appropriately. Now, there are a bunch of parts to the IDE, Integrated Development Environment, that you should pay attention to. In this main window, we have the editing area. In this window off on the right, we have what's called the Workspace. The Workspace allows you to display memory values, and it's a lazy language in that values are instantiated as they are defined and as they are executed. And so here in this window below, that's the command window. In the command window, at the command line, you can enter in commands, and the system will respond for you. You'll notice here that I have a vector here in the Workspace. Now, of course, if I double-click on this quantity in the Workspace, I actually see the contents, and while I'm running my program, I can halt my program or set a breakpoint, stop it, change the value, and you'll see that the value updates. So here, if I change this to 3 and hit enter, you notice it changes over there. And now when I get rid of that window, it's now, I can type this vector again, back, and you see that it has changed in the command window. So that's a vector. And you'll notice when I said vec equals, and I gave each of these numbers, 1, 2, 3, 4, those are the columns within an individual row. But if I wanted to specify the individual rows within a column, I say semicolon to define the next row. So if I said 1, semicolon, 2, semicolon, 3, and then 4, and I type vec again, it gives me a column vector. And so that's how I can specify a vector. I can specify a matrix, the matrix, and let's say I have the first row of the matrix is 1, 2, 3, and then the next row, I say semicolon, 4, 5, 6, and then the next row, 7, 8, 9. I could have another row, 10, 11, 12. So I hit enter, and I end this command with semicolon. If I type the matrix, well, there's my matrix. Now, this particular matrix that I defined, it's 4 rows by 3 columns. It's a 4 by 3 matrix. Now, of course, I can type that matrix out. I can also measure the size. So I'm going to call a function called size, vector, vec, and it returns back, it's a 4 by 1. If I say size, the matrix shows me it's a 4 by 3. So here's my vector. I changed it to a column vector. It's 4 rows and 1 column. So now, if I want to compute the transpose of a vector, I say vec t, the transpose, is equal to vec, and I say single quote, and that's the transpose. So if I take vec t and I type it out, that's, again, the row vector. With our matrix, well, here's my matrix, the matrix. So it is a 4 by 3. I can say the matrix transpose is equal to the matrix quote. And if I type the matrix transpose, it's now a 3 by 4. I can take the size of the matrix transpose, and lo and behold, it's a 3 by 4 matrix. So now what I can do, here's my vector. Let me set it back to a row vector. Well, let's set it to keep it as a column vector. So we have the column vector 1, 2, 3, 4. And if I wanted to multiply this vector, this 4 by 1 vector, and let me look at my matrix, the matrix, it's a 4 by 3 matrix. So if I have a 4 by 1, I could only multiply a 1 by 4. So let me go back to my row vector. So I say vec is equal to 1, 2, 3, 4. So that's a 1 by 4 size of vector. Now I can multiply this 1 by 4 vector times this 4 by 1 matrix. So I can say product, the product is equal to, and I'll say vec times the matrix. And the result, the product, is the resulting product. And so if you actually did that out, you'd find it's correct. We have 70 as the first one. And so if we took our vector and we multiplied 1 times 1, it's 1 plus 2 times 4, 1 plus 8 is 9, plus 3 times 7, that's 21, plus 21 plus 9, that's 30. 30 plus 4 times 10 plus 40, that's 70. So yes, 70. So it is doing the matrix vector product. So we can multiply vectors, we can multiply matrices, all that good stuff. So we can define variables. Let's say vec is equal to 1, 2, 3, 4. And then we say the matrix is equal to, and we need a 4 by 1. So let's say 1, 2, 3, 4, 5, 6. The rank for the matrix has to start as 4, 7, 8, 9, and 10, 11, 12. Okay. So now that we do that, let's see the product is equal to vec times the matrix. And you can actually cut and paste from your command window and test it out in the command window. And then once you know it works, you just cut and paste it into your program and then run it. So let's save this. And let's just say display in quotes done to give some output so that we know that it's running. And save. Let me set a breakpoint. You can set a breakpoint. You click on the line number for executable code here. It's everything with a tick mark. And let's run this. So we see vector, 1, 2, 3, 4, the matrix, and then the product, just as we had done in the command window. So now you can have if statements. So let's say you wanted to know if the first position of that product is 1 by 3, if it's equal to greater than 70, for example. So let's say threshold equals 70, and for example, we'll say if, and we'll say the product, and this is how you reference elements of a matrix, position 1, comma 1 is greater than the threshold, then end, and what are we going to do? We're going to display the message, yep, it is greater, otherwise, else, and we'll say display, no, it is not greater. Okay, so now let's save that. Oops, we forgot that closing quote. So we save that, we run it, and let's remove our breakpoint. Let's remove that done. We don't need that there. So let's quit, let's resave it, and let's run. It is not greater. It is equal to 70. So let's now make this one 2. Let's make it greater than 70. So, yep, it is greater. So if we make it 1, it's not greater. Okay. So here, when we say the product, 1, comma 1, if we look at the product, row 1, comma, column 1 is going to be 70. Row 1, column 2 is going to be 80. Row 1, column 3 is going to be 90. You can also call functions that return multiple values. So when we said size, the product, it gave us 2 values. Now, you can capture those in variables. We say rows, calls, the number of rows and columns, is equal to size of the product. So now we get rows is set as 1, calls is set as 3. So we're assigning in order to these variables the returns from the multiple returns from that function called size. So now we can say the rows calls is equal to size of the product. And now we'll say formatted string message equals printf. And we'll say the rank of the product is %d by %d. %d means it's a decimal. And so it's going to get that decimal value, rows and columns. And so now when we do the display, we're just going to display that formatted message string. And this is like a printf from block structured languages. Okay, so we run this, and we see the rank of the product is 1 by 3. It is not greater in this case. Change that to 2. We save. It is now greater than 70 for that first position. It is greater. The rank of the product is 1 by 3. So this is if else. We can say if, else if, else if, else, if we choose to. Now, we also can read in data with a command called CSV read, and I'll just demonstrate that a little bit later. But let's take a look at looping. We can say for I goes from 1, incrementing by 1, and I like to put that up to some num of iterations of the loop, end. So we're going to define a variable, and this variable is called num iterations, and we're going to define that to be 10. So now, inside of this loop, we're going to say message equals printf. The iteration is %d, because it's a decimal. We close the string, and we give it that loop index I. So display message. Okay, so now we're going to get a printout of all of our iterations. Of course, if we incremented by 2, it's going to start at 1, increment by 2 until it hits the bound. So we do that again, 1, 3, 5, 7, 9. Now it just so happens in Matlab, you can just type 1:1:10, and it'll just give you that list. Okay, so that's a little bit about looping. So let's now move on to a more sophisticated example, and we're going to use the reading of a file, and this file is customer data that I have created synthetically. And so let's take a look first at this historical customer data. This historical customer data, it's a CSV file, comma separated value, and so it consists of text, and this text has 3 columns and 200 rows. Now, you'll notice here, the first column is a number, second column is a number, and the third column is a number that's either +1 or -1. This is a data file, and the data file is going to represent the salary of an individual and the number of years in residence, whereas that third column is going to be the class label, +1 or -1. And that +1 or -1 represents whether or not someone was a good credit risk. So this is an example of the credit classification problem that we talked about. And so we're going to make the assumption, which I've done, is that the first 100 individuals are the positive examples, those who were approved for a mortgage from the historical data of the bank, and the next 100 records are the negative examples. So the number of points per category is going to be equal to 100. So I generate start a random number generator, the Mersenne twister, with a seed of 0 because I want to repeat or have a repeatable random number sequence. So I start out and I read the CSV file. And after reading that CSV file, CSV read, what I get, let me run that, is a table in memory. It's a matrix, and it has 200 rows because there are 100 positive examples followed by 100 negative examples, and it has 3 columns. The first 2 columns are the features, and the second 2 columns, the last column rather, is the class label assigned by the ground truth target function. So now what I'm going to do is I'm going to separate the 2-dimensional feature set for the positive examples versus the negative examples. So the positive examples are the first one through the 100th one, and I take the first feature, and the first one through the 100th row, I take the second feature. Then I do the same thing for the negative examples. I take the next 100. So it's going to be the first 100 plus 1 on through 200. First feature, do the same for the second feature. So now I put together just the features that describe the customer data, the years in residence and the annual salary. And I then create a separate vector with all of the so-called label targets. And you'll notice here I say all data, which is my table, and I say colon, which is wildcard. I don't care what row, but the third column. So it's going to take out the third column, every single row from 1 to 200 in that data file. And so, or that matrix in memory. And those are my targets. So now I want to change my points from being one data point describing a customer in each row to be one data point describing a customer in each column. So I want to make this matrix, instead of a row matrix, I want to make it into a column matrix. So I just invert that, or not rather, I take the transpose. So points is equal to PTS transpose. Likewise for the target, I want to turn that from a column vector to a row vector. So I just say targets is equal to TGT transpose. So now what I'm going to do is I want to plot my data. So I'm going to take my data, both the positive and the negative points, and I'm going to plot them in 2 dimensions. And so my first dimension, the positive points, I'm going to plot with a blue plus symbol, and my negative points, I'm going to color that as a red X. And so now I give that graph a title, turn on a grid, and I use some LaTeX to make it look nice. LaTeX is a document editor. And the horizontal component, the first feature, that's going to be years in residence. And the second feature, that's going to be the salary. And that salary is in units of 1,000. So let's run through that, continue, and let's look at the graph. And so this is the graph we get. Let me make that a little bit bigger. And you see here in my 2D graph, the horizontal axis, my first feature, is years in residence. And the vertical axis is salary in units of 1,000. So each data point in 2-dimensional feature space corresponds to somebody with a certain number of years in residence and a certain number of thousands annual salary. Okay. And you notice here the positive examples are these blue points, and the negative examples are these red points. Okay. So now that I have that, let me just make that a little bit smaller, put it on the side here. I'm going to go ahead and create a weight value, W, that's going to absorb the threshold for credit approval. I'm going to initialize it to some value, and then I have weight value W1 and W2 that I'm just going to initialize. So in a series of iterations, what I'm going to do is I'm going to augment my weight vector, and then I'm also going to augment my data. Now, when I augment my weight vector, I just create a W0. When I augment my data vector, my data points, I'm going to add an x naught, and each x naught is going to have a value of 1. And so I take my vector here, I create a vector of zeros, 1 for each example, and then it's all zeros, so I add 1 to it to create that 1 vector. So now that I do that, I'm going to start out and I'm going to randomize the modification of my weight vectors. I'm going to iterate some number of times and do the PLA update rule. And the PLA update rule says W gets W plus YI times XI. And I start out and I build my augmented data set. And how I'm going to build my augmented data set is I'm going to take each of the features as columns. So here's my x1, x2, up through x big N. Now, because I'm only in two-dimensional feature space, it's x1 and x2. And I'm going to insert a new column in the beginning and call that my x naught. And it's the same x naught that's fixed to 1. So I create what I call my x augmented. And I'm going to set x naught here, that vector, column vector, as the first part, the first column of this column matrix. And then I have all my other points as the remaining columns. So I'm building a matrix here. A block is my points, and my column vector here, x naught, that's going to be my augmentation. So let me continue here. And you'll notice here, when I say x naught, it's 1 by 200. It's a row vector, rather. And there are my points. My points are in row major. Okay. So I line them all up. And then I build my W vector. And my W vector has W naught, W1, W2. And then I'm going to set a learning rate. And that learning rate is going to lessen or shut down a little bit, soften up the PLA update. So now my hypothesis is equal to sine W transpose X. So it's sine of the augmented W vector times X. All right. Now, of course, I changed it up a little bit from W transpose because the ranks have to match up. So I do that, and then I pull up a figure, and I plot my data, the positive and the negative examples, and then I'm going to do my update. Now, in my update, this isn't completely the PLA update rule. That's going to be an assignment for you to implement. I randomly select one of my data points. Now, in the actual PLA update, you're only going to select from among the incorrectly classified points, not from all points. So I randomly select a data point in this example, and I set my learning rule, and I save my old version of my W vector. And again, the update rule, W gets W plus YI XI. And of course, I multiply by eta because I don't want to do the full update, just a partial update, 0.1 amount of the update, because I want to see only a slight change. And so here, I have my targets, and that's going to be my YI. I'm going to select that randomized selection to be the YI, the label associated with that randomly selected X vector. Now again, it should be random among the misclassified, not random among all the data. And so before doing the PLA update, I'll just evaluate my hypothesis and just print it out just for some bookkeeping to demonstrate formatted printing. And then this is my update. I say my WVAC gets the WVAC plus eta YI times my XI. And of course, my XI just happened to be my randomized selection of the augmented X vectors. So I do that update for my new W, and when after I'm done, I use a linear model feature function in Matlab to plot the new version of the hypothesis in 2 dimensions. So I take the weight vectors part, the W1 and W2, I take my dummy W naught, which absorbs the threshold mathematically. I set that to be my bias, and I say plot PC, which is to plot the perceptron linear model, and I pause. So let's take a look at this. So I'm going to continue, and let me bring that figure up to the foreground figure. Figure 1. Here we go. Bring that up to the foreground. And so now, make that a little bit bigger. And let's continue with the plot, figure 1. So let's continue. All right, so let me bring the figure to the foreground. And there's my new hypothesis. So I'm going to get rid of that breakpoint, and just let it run for a while to show you the update. Continue. So it's pausing, and you can see the updates for the weights, and you see it searched through the space of hypotheses randomly, modulated by eta equals 0.1. Now, of course, in the real PLA update, PLA Perceptron Learning Algorithm, you're not going to randomly select one of the inputs. You're going to randomly select one of the inputs that was misclassified. And that's going to be part of your assignment to do the actual PLA update rule. But the framework is here to show you how to implement something like PLA. But the biggest part of this example is the visualization. All right. So let's end there. I will meet you back in PowerPoint. So we're back in PowerPoint, and we gave an example of Perceptron Learning Algorithm, or at least the beginnings of it, in Matlab, and went over a little bit of Matlab. So that's all I had for today. When we pick back up next time, we'll talk about multiple hypothesis case, extend that bounding approximation for Hoeffding's inequality, and then we will continue forward. So please make sure you're keeping up with the reading. Until then, have a great weekend, and I will see you all